So in the next few minutes here, I just want to talk about some of these additional treatments we already alluded to. And so remember my cartoon already, freshly cut, fresh cut. If you don't remember anything else I say, just remember that, okay? Freshly cut, fresh cut is what we want, okay. And when we talk about, okay, what are treatments to maintain fresh cut quality? I think you've seen this before. It becomes a little bit repetitive, but that's good. And you'll notice here we're talking now about some of the supplemental treatments, okay? Others have shown different sort of cartoons related with cellular integrity. And remember, the important thing there, we talk about the compartmentalization, right, of different what we call substrates. They could be like phenolics and acids and things. And then you have the living tissue where a lot of the enzymes would be located, right? And so we're always concerned in terms of achieving shelf life is maintaining that integrity. And we have membranes. We have membranes around the vacuole. We have membranes around the cell wall, and then the cell around the cell, and then we have a cell wall. So that membrane integrity becomes very important in terms of maintaining, for example, not achieving translucency, right? When we have translucency, where the membranes are beginning to break down. When the product senesces, the membranes are beginning to break down. So we're interested in maintaining that integrity. So what do we do in fresh cut? We destroy all that integrity because we're cutting things up. So the wounding, right? The wounding is going to induce this phenolic metabolism that leads to browning because now we're going to be mixing those substrates with the enzymes. So if we didn't wound the product, we wouldn't have that problem. So it's very clear we're inducing the problem and then we have to control it. So in my mind, this is sort of a simplified diagram of that process. And one is we have a particular amino acid. Okay, this is in the case of lettuce. And we have an enzyme called PAL. It's not our PAL, right? Okay, phenylalanine ammoniolase. And it makes some intermediary products. And then we have another enzyme in the presence of oxygen. So that's why when modified atmosphere packaging, we have lower oxygen, we reduce that enzyme activity. Then we make some other intermediate compounds that are more complex, and then we make these brown pigments that are very hard to know their structure because really they come from many different components, but they become brown and ugly, and that's what we're concerned about preventing, right, okay? So that's that development of the enzymatic browning, okay, that development of those uncyclic pigments, okay? Now, a colleague, Michael Saltveit, who in the past has participated in this workshop, spent a large part of his career studying phenolic metabolism in lettuce, yeah? And so this comes from a paper that he published last year, and this is his proposed pathway for pinking and browning in lettuce, okay? So those of you who are aficionados of chemistry and biochemistry, you'll appreciate that. The rest of you may not, but what you'll remember is that if you know lettuce, you know that in the discoloration on the cut edges, we don't always get the same color. Sometimes we get transitory color. Sometimes we get more of a greenish color. And so that depending on exactly what combines, we can have different colors. Sometimes we get a transitory pinkish color. It's very interesting, right? So there'll be a period of time where the lettuce is beginning to go pink before it turns brown. So this is his proposed pathway of how that happens. How we get the different colors depends on what are the particular phenolics and how they combine, okay? And so some of that he's done with like inhibitors and things like that to come up with this general scheme. But the important thing here is that in the end, we're going to get these reddish-brown pigmentations, okay? And now, this goes back to the scheme that I showed before, but now with a little bit different wrinkle. So again, my thinking is less complicated, okay? So again, I'm sort of more straight line. You can see that, okay? Here we go, okay? But basically, we have two types from a practical standpoint. We talk about type 1, and that is when we have this polyphenol oxidase present, but we have a low amount of phenolic initially, okay? So the phenolics are those compounds that are going to polymerize and make the brown pigments. But in lettuce, we have a little amount of that. But when we chop the lettuce, we stimulate that enzyme. So that enzyme we call the PAL, we say it is wound-induced. It can also be induced by ethylene, actually, yeah, okay? But so it's wound-induced. So we set into motion that pathway. Well, that type of browning takes days, okay? So that's why sometimes we can cut lettuce and evaluate it after 4 or 5 days at, say 36 degrees Fahrenheit, and we don't see browning because that process we're starting very early on, and it takes days for those brown pigments to form. Then we have the other type of browning where here we have plenty of the polyphenol oxidase, but we have lots of phenolics. So what are examples? Apples, root crops, potatoes. So already there, we're already somewhere here in the pathway, all right? Lots of PPO, and we've got these compounds, lots of phenolics in these compounds. So now we just have to do the polymerization step, right? So that browning occurs what? Very fast, minutes, okay? Yeah, and so very same overall process, but where we start in the process differs between the different products that we have, okay? But the basic reactions are the same, all right? So if we go back to and talk about these enzymes a little bit, here's one, okay? So again, it's the wounding or ethylene that will stimulate the PAL. When we were studying this many years ago, here's an example. This happens to be broccoli. And so we have slices of broccoli, we have pieces, and then we have finely chopped. So the more we chop up the product, we know the product deteriorates faster, but the more we stimulate that enzyme, right? Because again, it's wound induced, okay? So right there, the more we chop. And then the bottom graph here just shows different lettuces and how they have inherent differences in their ability to produce that enzyme, right? So we all know, for example, the low one is iceberg lettuce, and everyone knows, for example, that butterhead and some of the green leaf lettuces will tend to brown more, because then they have more of this enzyme activity, okay? And then you can see that there's a list here of all these factors affect then the development of that particular enzyme, okay? All right? So here's an example of wounding, okay? So here we have blades. We'll talk a little bit more about this tomorrow, but we have blades. And on the right, we have two examples of water jet cutting. So water jet cutting is like an erosion technology. So in that case, we're cutting between the cells. We're separating the cells rather than cutting through them as we would with a knife. So the less damage we do, basically that's what I want to say, the less damage we do to disrupt the cells, the less browning we get, right? Okay, so that whole idea, if we could cut the lettuce and do less damage, less disruption of the cells themselves, mixing those components, we would have less browning. And that's what that water jet cutting can do, because we're eroding between the cells more than we're cutting through the cells, which is interesting, yeah? Okay, because here, this is with no modified atmosphere. 18 days at 36 degrees Fahrenheit, no modified atmosphere, and you can see the difference on the cut ends, okay? Yeah, so potentially that could be useful. Okay, now, then the other key enzyme is this polyphenol oxidase, okay? It requires oxygen. It also has a copper in what's called the prosthetic group. So the enzyme has a very complicated structure, and it contains copper. So one way to control its activity is to remove the copper, and that is a strategy, right? Okay, so, but basically with the modified atmosphere packaging, we're controlling really the oxygen level, okay? All right, so now we have different types. Okay, so in these products, basically related with the PPO, we have the different types of lettuce that I already showed you. I don't know if this company still is in business, but they evaluated lots of varieties of peaches looking for those that had low browning potential. And in that case, we have the type 2, where we have more rapid browning, okay, because already we've got lots of phenolics. Usually in the fruits, it's type 2. Then you have these new products already. The Arctic apple was mentioned before, because here we have a very silencing of the PPO, a control of PPO, so we have very low PPO activity. And then after that came out Simplot with their innate potato, which again, we've suppressed the genes that control the development of the PPO, right? So those are very powerful technologies, because really then we can back off on the modified atmospheres because we have less propensity for browning, right? Okay. Okay, so now, how do we control the browning? So already we talked a little bit about, we have selection of cultivars or development of cultivars with genetic engineering, and handle it to reduce the browning potential, meaning don't damage it before we cut it, right, okay? And then what our main strategies from fresh cut would be low temperature, right, all right? And then secondly would be the modified atmosphere. And then in some cases, we are using these additional compounds or preservatives as a general term. And so we're gonna run through a few of these, no? Acidulants, reducing agents, and sort of what they do, just for you to have this information, okay? All right. So the acidulants, okay? So in all of these enzymes, the PPO and the PAL, they depend on the pH, how acid it is, okay? So if we make it more acidic, okay, so here the optimum is more neutral, but if we acidify the tissue, we reduce the activity of the enzyme. So that's one way then to reduce the browning potential, okay? So you know, citric acid, malic acid, there are different formulations in which we're applying the acids, and that helps to reduce the browning, okay? Yeah, all right? Okay. And then we have this group that's called reducing agents, where in this case, we have then the development, the phenols are becoming more oxidized, okay, yeah? So they're becoming more oxidized, and these agents, what they do is convert the more oxidized product back to more the original phenols. So what we're doing is it's on the pathway there to the browning, and we're reversing part of that using these reducing agents. When we do that, though, we use up the reducing agents. So some very powerful ones are ascorbic acid and cysteine, okay? And right now I'm thinking about the question that was asked this morning. So everything costs, right? So these strategies are fairly expensive compared to the modified atmosphere packaging, because that's serving various purposes, right? Okay, so for vegetables, we rely on that. Okay, but ascorbic acid, cysteine, and then there are other groups that can have a similar effect of regressing the more oxidized phenolics back to simple phenolics. And there are several commercial products. I'm not giving a commercial to this one, but this has been in the fresh cut industry for a long time. NatureSeal, which has different formulations. Actually, it was a group from USDA that started working on this, and then it went developed into a company, right? Okay, NatureSeal. So they have different formulations, and a lot of it is calcium ascorbate related, and we're going to talk about the role of calcium, okay? So here's your reducing agent, your ascorbate, no? And so they have different formulations for different products, and they have a website there. But again, there are other companies with products. I just didn't include them, okay? So then there's another group called chelating agents, and remember I told you about the PPO. For it to act, it has a copper ion. So if we have a compound that'll suck up the copper, chelate it, we say, then that renders the PPO inactive. So that's another powerful way of doing it. And then there's another set called complexing agents, which as far as I know are not used in fresh cut, okay? And then there's a group especially the sulfites. There are some others like resorcinol, which is not used in fresh cut, but it's used on shrimp. And so these inhibit the enzyme, okay? But notice that first statement. They're very effective, but they're banned on fresh fruits and vegetables. I think in potatoes, low concentrations are allowed. Why? Because we don't eat potatoes raw. So they're cooked, and therefore we drive off the sulfites, okay? But in fresh fruits and vegetables, they're not allowed. But sulfites are very powerful inhibitors of the activity of PPO, okay? Now, and I'm going to show you an example here. So a few years back, I had a student. I really hadn't done work on fresh cut potatoes. I didn't really want to, but I had a student who wanted to work on potatoes, so okay. And so what we decided to do was, we know that sulfites are very powerful control of the browning. So here on the left, we have no atmosphere. So there's a red line here. So let's look on the left here. So this is an air. So these are cut pieces of potato, and they're like a russet potato, I think. Yeah, russet potato. And then we have the bisulfite, okay? And it was 0.2%, okay, sodium bisulfite. And then we were looking for combinations, and here we're looking for a controlled atmosphere, and then we had a combination with our ascorbic acid, right? Okay, so citric acid and ascorbic acid and a CA. So we were doing several things. So what we were trying to do is come up with a combination that was as good as the sulfites. Well, I think you can see from the photos we were never quite successful, right? Okay, yeah, so, so the sulfite really is very powerful, but that's what we're looking for, a better combination. Now on the right-hand side, I'm sorry, this is right here in this column, the third column, is citric acid plus ascorbic acid, I'm sorry. Now on the right-hand side of the red line is the controlled atmosphere, and the controlled atmosphere was 3% oxygen, 10% CO2, and I can tell you that that's not ideal. That's still a lot of oxygen, okay, although the CO2 is pretty good, so probably commercially we would be working with lower oxygen levels, okay, but it provides some benefit. So now you can see, if you compare the air controls, you can see it's a little better, but you can see how good the bisulfite is compared with our other treatment. So just to kind of put those into perspective, it was very hard, we couldn't come up with a combination that was as good as the bisulfite. Nevertheless, it's not allowed because some people are allergic to it, right? And so because of that, it's not allowed on fruits and vegetables, okay. Okay, so It's, yeah, no longer grass meaning generally recognized as safe, okay, by the FDA. At one time, it was more widely used, okay? Okay, and now here, I want to say something about this category, which to me is still a puzzle. As many years, we have a colleague who recently retired, was in fruit and vegetable processing, Diane Barrett. So she worked more with processing treatments and processing aids and things, and she would talk about this. But I'll tell you, I've read the relevant sections here on the legal aspect here of what's allowed, but you make this distinction between processing aid versus processing treatment. And so here's from the Code of Federal Regulations, right? And so here, if it is a processing treatment, like we're talking about, we're going to apply the nature seal, right? Calcium ascorbate. What does that imply? We must label it, right? Because we're applying a treatment. But if it's a processing aid, it doesn't have to be labeled. So there's kind of what we call a gray area there in practice, right? Maybe some of you can expound upon that, okay? Okay, so here are some examples, okay? The substance may be added to a food during processing, and here it would be like activated charcoal. So it's in the process, but it's not in the product in the finished form. Here they might adjust the pH. So to me, that's a processing aid. You're making a pH adjustment, okay? And then here, they're adding a preservative that is added to an ingredient. That may also be considered a processing aid. But really, again, to me, there's kind of a gray area there between what is actually a treatment and what is a processing aid, just to kind of raise that issue. Then there's a host of other anti-browning agents, yeah? And these have been reported in the literature. One is methyl jasmonate. Another is pineapple juice. It's very acidic, yeah? And so that's been used. We did some work using ethanol, okay, on our cut sunchokes here, and bingo, wow. You know, we could come up with some treatments there that really prevented the browning, right? That's not a commercial treatment, no, but it worked, okay? So the point here is that carbon monoxide, pretty dangerous though for us, right? So, you know, there are treatments that work, but in practice haven't been applied. But maybe under certain situations they could be useful, okay? Any questions or comments about that? I know that's very fast, but just to kind of give an overview of the topic, yeah? Any questions, comments? No? All right. All right, let me finish with a few comments about texture and basically the use of some of the calcium compounds to modify texture. So, of course, we know that texture is an important component. We want to retain the integrity and the texture of our products, right? And so a lot of things will affect texture, okay? And so we have a very complicated, the cell walls have a very complicated structure. There's a cartoon here, okay? But it's very complicated between cellulose and you have other, what we call hemicelluloses that link together. Then you have a lot of cell wall enzymes, okay? So all of that interaction affects the texture as well as turgor pressure, okay? So if a product is fully turgid, has lots of water, it's going to be crispier, also more fragile than if the product is slightly dehydrated. And that's something we haven't worked very well with, but think of, for example, spinach. Sometimes we want this, we harvest spinach when it's very cool, the product is very turgid, it breaks very easily. So if we can dehydrate, for example, using vacuum cooling, then we remove a little bit of the moisture. Now when it goes to the process line, it's less fragile because we've modified the texture, okay? So that has to do with the cell wall turgor pressure, okay, and the water content, okay? So there are many factors there that affect the texture of the products, okay? So another thing is, again, you've seen this kind of before, some nice photos that Jeff Breck showed, I think, is about the cell wall. So here we have one cell and we have another cell. And so they're next to each other. And then we have what we call this middle lamella, which is kind of like a glue, right? Kind of sticks them together. And that's where many of the enzymes act, and we get a separation then of the cell walls, right? And so we can reinforce that structure. If the cells separate like that, we tend to get mealiness, okay? Yeah, rather than when biting through and breaking through the cells, we get juiciness. So we really want to keep those cells, you know, together for that juicy phenomenon, okay? And we can reinforce that by adding a little bit of calcium to try to maintain the cells together, okay? And so calcium has been used in fresh cut. There are quite a few papers showing that it can be useful. And so one of the things here, of course, it must be labeled because now this would be a treatment, okay? And this is the concentration that could be used typically, yeah, okay? And then notice one thing here. It may impart a bitter flavor. So again, our colleague Diane Barrett worked with other sources of calcium, calcium lactate, calcium ascorbate, but it turns out calcium chloride is the cheapest, yeah, right? So You know, that has an advantage. So it's all about not having too high of a calcium concentration because you can impart a bitterness to the product. So what's an example? This is one that I did on melons, okay? So what is the advantage then of adding the calcium salt? So right here we have 4 varieties, unfortunately, okay? So just kind of, you know, you can see they're different colors. But we have different calcium chloride dips. So basically these were cut pieces that we dipped into a solution, okay? And so here we have 0, and now you can see the firmness. This is 2 days at 41 degrees Fahrenheit, okay? And then you can see we add a little bit of calcium, 0.25%, and you can see we got a bump up in the texture. In other words, how much force it took to puncture through that piece, right? So it would be a little bit crispier, right, okay? If we add 0.5, a little bit more, you can see generally, and then you can see 1. But notice the big difference really was between the 0 and the 0.25 initially. Now, if we store it for a little bit longer, here we're at 8 days at 41, you can see that indeed the texture has softened. Okay, here we have the 0 not treated, and you can see how now the force to make the penetration, the puncture through the fruit is less, right? The fruit has softened. And then you can see here how the calcium also provided, helped to retain then the texture of the fruit, okay? So that would be one of the reasons to use something like the calcium chloride, okay? To help maintain the firmness, okay? Now another benefit here is noted here, and we found that also in cantaloupe melons. You'll tend to reduce the problem of translucency, okay? Because the calcium also, not only will it firm up the cell wall structure, but it also has an effect on membrane integrity, right? Because there are some calcium ions in the membrane. So it has to do with membrane integrity, and that's how we would explain that we get less translucency by providing those treatments, okay? Now, Beth Mitchum and Diane Barrett and a graduate student whose name I have difficulty pronouncing, so I won't, but you can read it right there, is worked on mango. And one of the studies, they did look at calcium chloride, and they found they used a treatment of equivalent of about 1.5%, and they were looking at different varieties and the timing in order to come up with what would be a good scenario there, what would be a good treatment then if you provided calcium, okay? All right? Now, so again, we're going to go back to the nature seal here, where then those compounds help to maintain texture as well as retard the surface discoloration, okay? And of course, sometimes in some of these cases, they can incorporate other components. Then the last thing to mention, but it's already been mentioned today, and that's the use of this 1-MCP. And remember then that compound is going to block ethylene. So it's going to sit in the ethylene binding sites and inhibit then effects of ethylene because it's already blocking the ethylene binding sites. And so Beth Mitchum already talked about this a little bit. And so just to mention that, yes, you know, it's been applied to the cut products. So let me just skip over to this. This is a little bit on the honeydew, cantaloupe, and watermelon. And so it is clear that, especially in watermelon, it can have a benefit. But at least when we worked on it with fresh cut cantaloupe and honeydew, we found little benefit. But we were at low temperature, for example, okay? So, you know, the devil is in the details there. You'll see studies that purport that, yes, that 1-MCP treatment had a big effect on the quality of the fresh cut product. And then other studies, it only had slight effects on firmness. And that's really what we found, was it had slight effects on firmness on the melons, okay? But on watermelon, it would have a greater effect, okay? So these supplemental treatments, and there probably are others that we didn't talk about, but mainly I wanted to focus on the ones regarding the browning and how we control that, and a little bit about the texture. And so because of the labeling requirements, so remember, these are treatments and they must be labeled, and so we tend to use them little. Notice here, this company, Simply Fresh. Our name says it all, right? Simply Fresh, no additives, right? So when we think of fresh cut, I think there is that idea. We don't want to add a compound, a treatment, if we don't have to, right? Only in the case of maybe apples, for example, many of the varieties, because they brown so quickly, we are providing a chemical treatment, right? As well as modified atmosphere packaging. But if we don't need to apply something, we certainly don't want to, okay? So in order not to, then yes, we're looking at the genetics, the maturity, the conditioning to minimize the need for those treatments, right? And again, like in the case of the calcium, we want to pay attention to then, if we were interested in that, use as low concentrations as possible in order not to affect the flavor of it, okay? And yeah, And I think that's basically what I wanted to say about that. And there is a list of references. Some of these are not so recent, but they're very good references that give you a good overview, I think, of this topic, okay? So thank you for your time. Yeah.